Hello AP Chemistry and welcome to 16.6 Weak Acids Part 2, picking up with the concept of comparing strong acids versus weak acids in this figure from your book. Alright, so looking at what your figure says, so here we have some 1 molar HCl and some 1 molar acetic acid, right? So the only difference really being is that here we have strong acid and here we have weak acid, but it's the same concentration, right? Which means that same total moles. Yes, that part is key, right? Same total moles. But if we look at this figure, what's different is the number of moles initially available for reaction. Yes, the number of moles initially available, right? Because, okay, just to be clear, right, if we think about the net, right, the net's going to look like this, right? It's going to give us that, right? It's going to give us some H2 gas plus some Mg2 plus, right? That's what the net ionic says, right? And so if we think about the implications here, right, this one has much less H plus versus this one immediately available, right? And if we look, when these pieces of magnesium are dropped in here, we see that, right? Because we see this one starts to react, but this one might say, reacts rapidly, right? Because we have those larger bubbles, right? Larger bubbles, and the reaction is complete much faster. Yes, there is no longer any magnesium, and we can still see those itty bitty tiny bubbles happening in the weak acid one, right? And if we think back to last year, I think we might have seen this in something, right? Wherein those little tiny bubbles, right, make the whole thing look white, right? Where your first initial reaction say, ooh, it turned white, but it didn't, right? That's just what happens when we have whole boatloads of tiny bubbles present, right? Versus these big old giant bubbles. But eventually the point is that it all reacts in the end, yes? The reaction goes to completion because this is the kind of reaction with a ginormous K value that goes to completion, yes? Does that make sense? But the rate, right, of the reaction, which is determined by, ding, 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 the concentration of the species at the beginning, right, affects the rate of the reaction, yes? As in there's less of my H plus immediately available, so it reacts, and then the reaction shifts forward, and by reaction I mean dissociation of acetic acid, shifts forward and more H plus is produced and it's consumed, produced and consumed, right? So it's basically like a, the Shat process that keeps happening over and over again. Kind of, right? Kind of. All right, next up, here's your graph from the book, right, that deals with percent ionization versus the molarity of my solution, right? So here is the hydrolysis for acetic acid, right? So if we think about this, right, we have our Ka, and here is this part, right, over our, this, right? Now, when we look at this graph, what it says, right, is that at, very low molarities, we have a lot ionized, right? At relatively high molarities, right, less of it is ionized, right? And if we think about it, right, we can look at this from a Q versus K perspective, right? So for example, if we were starting here at 1, if we're going to go from 1 to 0.05, what we have really done, if we started with a 0.1 molar solution and we were to cut it to 0.05, really it means we're diluting it in half, yes? We are adding water, right? Now, at first glance, one would say, well, this is not K versus Q because we're adding water, and water is not part of our expression. But water affects the, right, water affects the molarities of every other species, right? So if I were to add water such that the concentration were to cut in half, right? And I think about what effect that has here, right? Because I have 2 terms on the top and only 1 term on the bottom, what that means is that my Q is now less than my K, yes? If I were to dilute it from 0.1 to 0.05, at that moment, Q is less than K, yes? Q is less than K, right? Because I'm diluting 2 terms up top and only 1 term on the bottom, which means that my Q value is smaller. Go ahead and plug some numbers if they're in there if it would make you feel better, right? Which means that instantaneously Q is less than K, which means the reaction shifts forward, right? And if the reaction is going to shift forward, we're going to produce more H3O plus and acetate ion, which means we're going to end up with a higher, right, percent ionization than where we were originally. Yes, does that make sense? All right, and note that this is very important because we come back to this, except now we give it a formal name in chapter 17, the common ion effect, basically is what we're talking about. All right, quick practice exercise. So in 1611, we found that the percent niacin is that. Calculate the percentage of a niacin molecules ionized in a solution that is that and that. So really that's the same math that we did before, and then the percent ionization. So I'm just going to assume you can solve these, and obviously it's going to follow this trend. All right, last up, that brings us to polyprotic acids, right? And this is one of those beautiful terms wherein the definition is in the term, yes, many proton acids, right? It's an acid with more than one acidic proton. Here, it's really important, right? Because if there's more than one acidic proton, oh my gosh, there's going to be more than one Ka value. Now, in order to know which Ka value corresponds to the math that we're trying to do, we need to be able to write the respective K expressions. So, if I have some carbonic acid, right? Actually, let's go ahead and get our water in there. So if I have some carbonic acid plus some water, right, that's going to give us some hydronium and some bicarbonate, right? That's what's going to happen first. And since that's the first dissociation, or the loss of the first proton from carbonic acid, this gets labeled as Ka1 of carbonic acid, right? Now, if I take that HCO3 minus and that were to further react, I would get this. And this would get labeled the Ka2 of carbonic acid. Yes? Ka1 versus Ka2 of carbonic acid. Now, when we talk about the dissociations, right, the first one happens completely, and then the next one happens, because if we look at the K values, right, so starting with carbonic acid, right, we'll see that, right, 4 times 10 to the negative 7th, right, and this is 5.6 times 10 to the negative 11th, right, which means, you know, relatively big difference, which means that Ka2 doesn't begin to affect our concentration at a significant level, right, until Ka1 is done. Yes, until we have fully dissociated carbonic acid into bicarbonate, then we have to consider the dissociation of carbonate into bicarbonate into carbonate, right? Your book gives you 10 to the third, right, as the difference to look out for, right? As in, as long as Ka1 versus Ka2 is 10 to the third difference, right? You don't have to worry about the subsequent Kas when you're doing 1, right? Whereas for something like citric acid, gets to be problematic because none of them are 10 to the third from each other, right? Which means that the math gets more complicated than you are ever going to be asked to do. Yes, does that make sense? Right. Okay. Thank you for listening to this last section on weak acids. Obviously, in the next section, we're going to take all of this discussion, and now we're going to flip it and do it backwards because we're going to talk about it from the perspective of weak bases. Same concepts, just now from the base perspective. All right, thank you for listening. Be good, and I will see you soon.